Hello everyone, I Goinda Gahine, lecturer in mining department at Chhattisgarh Swami Vivekanand Technical University, Bhilai. Today I will discuss lecture number 36. The topic is surface mine blast design. Following are the content of this topic. First one is introduction, second one is parameter of blast design, third one factor affecting surface blast design, fourth drilling pattern, next blasting pattern, then powder factor calculation, then adverse effect of surface blast. So, first introduction. This is meant to be a toolbox for blast design in conventional rock quarrying and open pit mines. This write up is not meant to give straight answer to the blast design parameter, as every single quarry is unique. However, the general relation between the main blasting parameters geology, blastability and explosives will be applicable, and the estimation model is a very good tool for planning, test, blast and experiment, and also for adjustment of the blast design when this is necessary for optimizing the quarry production line as time progresses. High accuracy throughout the whole blasting process is fundamental for achieving a proper blast result. So, rules of thumbs for blast design. Rule 1, the detonation velocity of the explosion should match as closely as possible the sonic velocity of the rock to be blasted. Rule 2, generally select the most dense explosive possible consistent with water loading condition and desired result. Rule 3, select explosive according to the characteristics of the rock formation to be blasted. Rule 4, when using slurry or water gel explosive, always determine the critical temperature below which the explosive will fail to reliably detonate. Guidelines for blasting geometry. Rule 1, the distance between hole means spacing should not be greater than one half the depth of the borehole. Rule 2, in any place where there is hole for hole delay, the spacing to burden relationship should be 7 to 5. Rule 3, steaming should be equal to the burden. Rule 4, sub drill if necessary should be between 0.3 and 0.5 of spacing. Parameter of blast design. So, in which first drill burden is defined as the distance between the individual rows of hole. It is also used to describe the distance from the front row of hole to the free face. When the bench face is not vertical, the burden on this front row of hole varies from crest to toe. Spacing, it is distance between hole in any given rows. Next, subgrade. Generally, the hole are drilled below the desired final grade. This descent is referred to as the subgrade drilling or simply the subgrade drill. Next, steaming. A certain length of hole near the collar is left uncharged. This will be referred to as the steaming length T, whether or not it is left unfilled or filled with drill cuttings or crushed rock. Then bench height H is the vertical height from the toe to the crest. Next, drill length is equal to the bench height plus the sub drill. Length of explosive column LE is equal to the hole length minus the steaming. This column may be divided into section deck containing explosive of various strength separated by length of steaming. Then bench height. Bench height is decided by first production required, second type of deposit, third thickness, fourth geology, fifth quality, sixth equipment. Next, burden. Some important empirical formula for burden: B is equal to 24 into D plus 0.85 Utukari, B is equal to 25 minus 30 into D Hagen, B is equal to K into D into P into T the power 0.5 peers, where K is equal to constants, its value is 0.7 to 1, more for weak rock, where P is equal to peak explosive pressure kg per centimeter square, T is equal to tensile strength of rock kg per centimeter square. Burden is generally 25 to 40% of bench height depending upon rock, properties, fragmentation and explosive used. Spacing: generally we take spacing as 1.1 to 1.5 times of burden. Subgate drilling: holes are drilled longer than bench height to avoid toe problem. This extra drilling is called as subgate drilling. So, H d is equal to 0.1 into H and H d is equal to 0.3 into B. Parameters of blast design. So, other parameters are powder factor, steaming and decking, delay timing, decoupling ratio, base charge, column charge. Look at the figure. In the figure, the all parameters are shown like spacing, then burden, then angle of face, free face, subgate drill and successive drill holes, toe, crest, etc. This is the whole parameter are shown in this figure, and the topmost strike line shows the bench. Factor affecting surface blast design. The controllable variable are first hole diameter, then hole depth, then subgrade drilling depth, then steaming distance, then steaming material, then burden and spacing, then number of hole in the blast, then direction of rock movement, then timing and types of explosive and inertiation system. Look at the figure, the pattern in quarry or open pit. In the figure, in which showing the bench height, burden, spacing, hole length, subgrade, steaming and hole diameters. These are showing the exact parameters on surface blast design. The following are the some of the important factors which generally governs for blast design. First, physio-mechanical property of rock. Here, type of rocks, dynamic tensile strength, compressive strength, Young's modulus, Poisson ratios, density and hardness of the rock mass, presence of discontinuities, bedding planes and joints, etc. are very important. Then geology, in which pit geometry. Under these headings, thickness of coal seam or ore body and bench height over burden bench height, bench slope angle, strip width, height to width ratio and length to width ratio are generally considered. Explosive characteristics. Factors generally considered under these headings are type of explosive, type of booster, bulk strength, energy release, per unit mass of explosive, detonation pressure, explosion pressure ratio of decoupling, strength of explosive used, time taken for explosive, wave to travel to the free face and back volume of gases product per unit mass of the explosive, velocity of detonation, velocity of explosion propagation, explosion wavelength, weight strength, number of sparks that an explosive wave may produce, length, diameter and weight of the cartridge, loading density, bottom charge and column charge density, etc. are very important characteristics of blasting accessories. Types, thermal properties are also important. Next, blasting techniques. Here, objective of blasting, drilling pattern, number of availability of free phase, manner of charging, charge per hole and per delay, sequencing of inertiation, etc. Delay between two holes in a row and delay between two row, decking, length of explosive column, height of the bottom charge, volume of the explosive in the blast hole, etc. are to be considered. Next, powder factor. The powder factor is defined as the explosive necessary to fragment 1 meter cube of rock. This equation can also be defined as the amount of explosive over the cubic yard of material desired to be blasted. Kg of explosive used per volume of material blasted is equal to kg per meter cube. It is the opinion of many specialists this is not the best tool for designing a blast unless it is referring to pattern explosive or expressed as energetic consumptions. The size of the fragmented rock should match the bucket size of the excavator and also the grizzly size of the primary crusher. It can be also expressed in ton per kg. Next, drilling pattern. The basic pattern of drill hole employed in open cast mine are square pattern, scattered or triangular pattern, single row blasting pattern, multi blasting pattern, wedge cut pattern, diagonal blasting pattern, then square pattern. This pattern can also be called as multi row pattern. The drill hole are drilled in row ones behind the other. Stagger or triangular pattern. The drill hole are drilled in rows. The second row hole are positions midway between the first row of the hole. You can see on the figure the actual staggered triangular pattern या square pattern. This is the drilling pattern, staggered pattern, in which the first row and the second rows, the distance and the sequence are changed. So, however, considering the pattern of the blasting, the pattern can be classified as follow. First, single row blasting pattern, second, multi row blasting pattern, third, wedge blasting pattern, fourth, diagonal blasting pattern. So, in first single row blasting pattern, the hole are defined in a single row, the specific explosive consumptions is low. The danger associated with fly rock is more than multi blasting pattern. The holes are drilled in several rows. The holes may be staggered or square. Look at the figure in which showing the spacing and trunk line then burden, then detonator, then safety fuse and delay. All the accessories and the parameters are shown in the figure. Then Vachkan pattern. This pattern as shown in the figure is adopted in hard and medium hard rock. The delay are fixed from the middle to the ends and shown in the figure. The center blast hole in the first row blast first, followed by the blast hole connected to the second hole from the center with delay number 1 and then in the sequentially order of the delay. The center blast hole in the first row blast first, followed by the blast holes connected to the second holes from the center with delay number 1 and then in the sequential order of the delay. You can see on the figure the actual wedge cut patterns sequence. Next, diagonal blasting pattern. This type of blasting pattern is carried out in benches where the cleavage plane of the rock is parallel to the length of the face. This pattern reduces secondary blasting and the blast hole can be drilled in square or staggered pattern. The delay must be planned in such a way that the blasting proceed from one side to the other. It must be ensured that the delay are in proper sequence to avoid any cutoff. Look at the figure. The actual pattern is showing on the figure means the diagonal blasting pattern. In open cast multi-row blasting, various delay inertiation sequence are possible. They are instantaneous, first, second, row delay and third V1 and V2 pattern. You can see on figure the pattern of instantaneous, row delay and V1 and V2. V1, V2 or V3 pattern, this pattern are far superior to row delay. This result in superior fragmentation due to reduced hole burden and increased spacing at the time of the hole inertiation and also due to in-flight collision of broken rock during its movement. The delay action of hole in the back row reduce over break, ensuring increased wall stability. The best available pattern in one where the hole are drilled stagger on a equilateral triangle pattern. This is a drill spacing to burden ratio of approximately 1.16. It has been observed that an effective spacing to burden ratio of about 3.5 is achieved with holes drilled on an equilateral triangle grid and fired using a V1 inertiation sequence. Look at the figure in which the showing the pattern of V type. Powder factor calculation. The next point. The quantity of explosive required per round of holes in an estimate only since it is a general practice to go by trial and error method. This is because of the variation in the physiological properties of the rock mass. However, the quantity of charge Q can be calculated by the formula Q is equal to E into H minus St into pi d square upon 4, where H depth of the hole, St height of the steaming columns, d diameter of the hole, E specific weight of the explosive. Specific consumption C of the explosive is equal to Q upon B S H kg per meter cube, where B burden, S spacing and h height of the charge. Powder factor P is equal to B S H upon Q meter cube per kg. The charge required per hole is first calculated considering the blast geometry and the powder factor. Then the total charge required can be easily calculated. Adverse effect of surface blast. The following are the adverse effect of blasting in surface mine. First, vibration, then air blast and fly rock. Explosive energy is used to break rock. However, the use of this energy is not 100% efficient. Some of the energy escapes into the atmosphere to generate air blast or air vibration. Some of the energy also leaves the blast site through the surface soil and bedrock in the form of ground vibration. Both air and ground vibration create waves that disturbs the mineral in which they travel. When these waves encounter a structure, they cause it to shake. Ground vibration enter the house through the basement and air blast enter the house through the wall and roof. Air blast may be audible noise or inaudible concussion, where outside a house the blast may be heard because of the noise. However, noise has little impact on the structure. The concussion waves causes the structure to shake and rattles object hanging on wall or sitting on sleeves. This interior noise will alarm and startle people living in the house. Fly rocks is debris erected from the blast site that is traveling through the air of along the ground. Fly rock is the single most dangerous adverse effect that can cause property damage and person injury or death. Ground vibration propagate away from a blast site as raylight or surface waves. This wave from a disturbance in the ground that displace particle of soil or rock as they pass by. Particle motion are quite complicated at the ground surface. Free boundary major particle motions have the greater displacement and displacement decrease with depth. At a depth of between 20 to 50 feet below ground surface, particle displacement are barely detectable. Structure that are well coupled to the ground tends to move with this motion. Structure buried in the ground are less affected by surface motion. Air blast is measured as a pressure in pound per square inch and is often reported in terms of decibel dB. Air blast is a pressure waves that may be audible or inaudible. Elevated air blast level are generated when explosive energy in the form gases escape from the detonating blast hole. Energy escapes either through the top steaming or through fracture in the rock along the face or at the ground surface. Air blasts radiate outward from the blast site in all directions and can travel long distance. Sound wave travels much slower, 11,000 feet per second, than ground vibration, about 5,000 to 20,000 feet per second. Hence, air blast arrives at off-site structure later than do ground vibration. Material that is erected from a blast site that travels through the air or along the ground. Fly rock may be rock or soil. Any size material is capable of damaging property or injury people. The single factor of surface mining that is most likely to cause a fatality. Fly rock control is essential. The blaster is responsible for securing the area around the blast site where fly rock debris may occur. Fly rock can be cast thousands of feet from a blast. The most dangerous source is ejection from a crack or weak zone in the high wall phase where gases violently vent. This action is akin to a rifle where the expanding gases eject a projectile. Frequently, the ejection of steaming out of the top of blast hole is called rifling. Fly rock damage is quite obvious when a structure is hit. Holes and marks are very visible. Thank you.